Hello everybody, my name is Pierre Le Maguerès. I am a single crystal crystallographer at Rigaku Americas Corporation. Before we get going, I would like to remind you that you can ask questions by writing using the Q&A section on the right-hand side of this interface. And then at the end of this presentation, I will take a few minutes before we log out to try to answer as many questions as I can, again, by writing. So my talk is going to be about powder data collection, but on the XtaLAB Synergy-S, which is a single crystal diffractometer. So I'll show how good powder data can indeed be collected on the Synergy-S, and I'll go through some of the benefits that such a system actually brings to the table. So this is what the Synergy-S looks like. On the left-hand side, you have a picture of the full system once it is within its enclosure. So that enclosure makes the system self-enclosed and X-ray foolproof. On the right-hand side, there is a picture of the goniometer itself. It is a standard design in the sense that you can swap sources or detectors without having to change anything to the design of the hardware. So on the source side, you can have one or two seal tubes. You can also have a rotating anode. And on the detector side, you can have any of the Rigaku family of detectors, the HyPix family, or you can also have some of the larger Pilatus or Eiger detectors. So let's have a brief overview of the hardware that makes that diffractometer, and let's start with the source. So the source is called the Photon Jet S. It is a micro focus seal tube, and we have specifically designed the optics to best fit the source so as to gather as many photons as we can to make up the beam. You have a choice of one or two wavelengths among copper, molybdenum, or silver. So that means that you can have a single source system or a dual source system where you would have a mixture of two wavelengths, these two wavelengths that can be chosen from these three choices. The beam generated by these seal tube sources is really small. Its full width at half medium is about 100 microns. So right there, it tells you that you'll have more flux, more photons onto smaller samples. The goniometer is called the universal goniometer. It's a full four-circle kappa goniometer. Therefore, it is highly flexible. Its sphere of confusion is 7 to 10 microns, and it can collect data as fast as 10 degrees per second. Data collection always being done along omega, which is the vertical axis. And then the detector. The detector is a HyPix detector. It's called an HPC detector, but also called a direct photon counting detector. So that means that it counts photon, it counts each and every photon that hits the detector, or as soon as it hits the detector, instead of integrating all the photons that hit a given pixel throughout an exposure like CCD and CMOS detectors do. So here the important words are direct photon counting versus photon integration or charge integration throughout the exposure. The picture shows a HyPix 6000 detector. This is a default detector configured on the Synergy-S, but you can certainly have any other of the Rigaku detectors. So let's see now what this hardware brings to the table in terms of powder data collection. Well, the first benefit, and one of the most important ones for sure, is the very small amount of sample that you can use for analysis. And this is due to the small beam that this macrofocus seal tube generates. Remember that the full width at half medium of the beam is about 100 microns. So this picture represents an ideal Gaussian-shaped beam. When you take the entire beam size into account, for us, this is about 300 microns, but that of course includes the tails of the beam, whereas the full width at half medium, as indicated by this gray box, is about 100 microns. So that means that on samples that are 100 microns in dimension, you will already have 50% of the full intensity of your beam. The second benefit is the convenience with which samples can be prepared and mounted and centered. And this is really due to the type of goniometer heads that are used on these single crystal diffractometers. And you see one of those goniometer heads here. So there are two ways of preparing samples with these goniometer heads. One of them, the first one, is to insert a stem within the goniometer head and then glue your sample at the tip of it. Now, instead of inserting a stem, you can insert a capillary that filled with powder. The other way to mount samples is to first insert a flat magnet inside the goniometer head, and then mount a stem that itself is already mounted on a magnetic base. And then at the tip of that stem, you would typically have a loop, which single crystallographers use to glue their crystal. But then instead of gluing a crystal onto the loop, you can fill the loop with powder. Here are some examples of capillary mounts. Quartz capillaries, but also Kapton capillaries can be used, and Kapton is much more X-ray transparent than quartz, and it will generate much less X-ray background on your diffraction images. And here are some examples of mounts, and then another example of capillary mounts here. Now, as I said a minute ago, you can also use loops. You can use Mightygen loops or fiber loops. And typically you will wet out the loop first with some paraffin oil, and then try to pack as much powder as possible within the wet loop. And once this is done, then you mount the loop and center it just like you would a crystal. Here is what a powder sample mounted in a loop looks like. On the far right, you see the thickness of that powder sample is 100 microns because that red circle represents an area with a diameter of 100 microns. So typically I use loops that have a diameter of 100 to 150 microns. Otherwise, larger loops tend to let the powder fall off. Then, of course, if you use that kind of mount, you have to turn off the cryo system first. Otherwise, the air blown by the cryo system will blow away the loop within the powder within the loop. All right, so next, let's talk about the hardware versatility. First, remember that you can have two sources on the Synergy-S, and if you do, then you have two wavelengths readily available to you, as shown by these two red arrows. So they are your two seal tubes, and therefore two wavelengths. And remember that you have the choice of copper, molybdenum, or silver for these two sources. Then you also have a temperature control readily available to you, because single crystal crystallographers usually collect their data at low temperature. So they use such a cryo device, which I'm highlighting here with my cursor, to cool down their sample to 100K or so. But of course, you can use that for your powder samples as well. In this case, though, you would mount your powder inside a capillary. So you can collect powder data at low temperature, but you can also collect a multi-tempered or run a multi-temperature experiment, whereby you would program in several set points or temperature set points and ask Chrysalis Pro to automatically collect a data set at each one of these temperature set points, because Chrysalis Pro controls both the diffractometer and the cryo system. So it will also automatically change temperature without any intervention from your part. Let's talk now about the goniometer. I told you that this is a full circle goniometer, which means that it has a kappa axis, and the kappa axis is the one that I'm highlighting with my cursor right now. So that kappa axis tilts the sample at different angles in the beam so that the sample can adopt different orientations. And so that would allow you to collect powder data according to Gandolfi strategies. And you would do that, of course, if your powder samples adopt or the grains of your powder samples adopt preferred orientations in the mount, and therefore you need doesn't give you enough of data randomization. So then you would collect the data sets by tilting your powder sample in different orientations in the beam and merge all the images together to get better powder or data randomization. The data collection interface in Chrysalis Pro is easy to use. What you see here on the screen is the only thing you have to learn in Chrysalis Pro to collect powder data. So these two red boxes indicate how to set up data collection according to Gandolfi methods. And here I decided to use 4 kappa settings, which means 4 different crystal or sample orientations in the beam. I set up my detector distance to 60 millimeters and decided to use a target resolution of 0.9 angstrom. And using all these settings, then Chrysalis Pro automatically collect or calculate strategy, so you will collect data across a given resolution range, basically. And you can access the strategy via this run list button. And when I do that, here is what I see. First, XtaLAB Pro has set up two or different detector positions to collect the high resolution data, and then another detector position to collect the low to medium resolution data. And it does that on each side of the beam, therefore the negative angles first and then the positive angles. Then for each one of these detector positions, there are 4 kappa settings or kappa angles associated with a different kappa angle per scan. And that's what will give you the better data randomization. And then the next thing to be aware of is that both phi and omega will rotate at the same time. On the right-hand side box, you see that a full 360 degrees rotation along phi is scheduled. And on the right-hand side box, you see the rotation range along omega set up for each scan. So rotating 2 axes instead of 1, here is how it translates onto a diffraction image. On the left-hand side, this is a diffraction image from silica that are obtained by rotating along omega, or the sample along omega only. And on the right-hand side, I rotated both phi and omega. So with the omega only rotation, you see that the intensity distribution along the rings is obviously pretty uneven, with parts of the rings being more intense than others. On the right-hand side now, with the phi and omega rotating at the same time, the intensity distribution along the rings is much more even, if not perfect now, but at least it's more even. Now remember that this is for only one image. Typically, you will collect, if you use the Gandolfi method, you will collect an image at different kappa settings. So then once XtaLAB Pro merges all these images collected at different kappa angles together, you will then get an even better data randomization. So let's talk a bit more about the detector now. So the detector is a HyPix 6000 HE. And again, this is a direct photon counting detector. So that means that it counts each photon that hits it and then discards it, instead of integrating all the photons that hit a given pixel throughout an exposure. So that has 2 consequences of interest to us. First, that direct photon counting technology increases the sensitivity of the detector while virtually eliminating almost all electronic noise. And the second consequence is that the point spread function for that detector is basically one single pixel. That means that all the photons that hit a given pixel will remain imprisoned on that pixel, instead of leaking across neighboring pixels, which is what happened with CCD and CMOS detectors. So I don't have the time to get into too much details here, but just know that with HPC detectors or direct photon counting detectors, X-ray photons are transformed immediately into an electrical signal via the generation of electron-hole pairs within the matrix in which the photons penetrate when they hit the detector. Then you apply a certain voltage difference to that matrix. So one type of charges moves one way while the other type moves the other way. And then you count one or the other. Here we count the plus charges on the electronics, with the electronics down here. So I want to point out that this whole process is unique to each pixel. That means that each pixel has its own readout line, and that's how we keep each pixel isolated from its neighbors. So as a result, where a CCD or CMOS detector will need a scintillator and a fiberglass taper even before photons are transformed into an electrical signal. Here we don't need those things because, again, X-rays are transformed into an electrical signal immediately. And the consequence of that is that there's no loss of data. There is virtually no electronic noise also, and that will greatly improve the I of a sigma statistics on your data. And of course, this is especially important for the weak data. So that gets me back to the fact that I said earlier that you can analyze small amounts of powders on the Synergy-S, primarily it was due to the small size of the beam, but the fact that the detector is so sensitive and will improve so much your signal to noise data, obviously helps also with small amount of samples. So you don't need to collect a dark current image before to start collecting. And then there is no leaking of X-ray photons across neighboring pixels, which means that there is no smearing of reflections. There's no enlargement of reflections. On these detectors, reflections or powder rings will remain much thinner. And that's what you get from the Rigaku and also the Dectris type of detector. So how does that translate into diffraction images? I have two examples to show you. That first example is a diffraction image obtained from silica, which I exposed to the copper beam for 60 seconds. And then on that image, I drew a horizontal line here, which gives me access to a two-dimensional plot of the intensity distribution along that line. And you see the line crosses over the beam stop shadow. So on the 2D profile, then I see that the intensity goes down to zero in the beam stop shadow. And that's how I can show you that there is no electronic noise coming from that detector. Otherwise, if there was, then that plot would not completely go back down to zero behind the beam stop. The second example is a diffraction image obtained of a protein crystal, which is tomatin. So tomatin crystallizes in a unit cell that has one long dimension of 150 angstroms. So we brought the detector to a close distance of 60 millimeters, and so that distance is really close related to that long unit cell edge dimension. And we made things even worse by choosing a large crystal, which itself will enlarge the size of the reflections. And so with all that taken into account, we wanted to see how the reflections would still be resolved on the face of the detector. So if you look at that area of the diffraction image, you see that the reflections look well enough resolved. Again, I drew a line along that row of reflections to get a two-dimensional plot of the intensity distribution along that line, and this is what I see. In between reflections, the intensity comes back down to zero or almost, showing that the reflections are well resolved enough. And sure enough, we got a beautiful structure out of that crystal. Now, in terms of resolution of data, you can even go further with the copper beam. And this is upon using an additional little piece of hardware, which is called a continuous beam divergence tuning device. It's a little slit that we move from the outside of the beam and progressively into the beam, so as to block more and more of the most divergent photons on the edge of the beam and keep only the more parallel photons in the center of the beam. And doing that, we decrease the divergence of the beam, which in turn decreases the size of the resolution of reflections or of powderings, as shown here by these black and red circles. So that will cause, or that will enable better peak separation. Sharper peaks, your peaks will have a smaller full width at half medium, and it is better than just changing the collimator, because when you change the collimator, you have no control of the size of the pinhole at the tip of the collimator. So most likely you take too much of a hit in terms of intensity, whereas with that slit divergence, you can actually move it slightly and into the beam, just what you need to resolve your reflections or your resolution peaks, and therefore you take much less of a hit in terms of intensity. Here is an example again of a protein crystal. Here, this time, this is a crystal of catalase, which has an even longer unit cell edge of almost 230 angstroms. This time, I brought the detector to 70 millimeters, which is really short again, according to that unit cell edge. And then, of course, with the full beam, then I couldn't see reflections. All I had is streaks of diffraction. Now, I started decreasing the divergence of the beam by moving that slit onto the beam little by little, and here is what I got. I moved it a little more, and then a little more. And then I stopped there because obviously here my reflections are now well enough resolved. Let me play that for you again. This is the full beam, and then I close the slit onto the beam a bit more, and then a bit more. And then I stop there. So moving that slit is easy to do from the Chrysalis Pro interface. There's a little dedicated dialog with a slide bar, and you slide that bar sideways to decide upon a new beam divergence, and then you stop whenever you think that your diffraction features are well resolved enough. In terms of powder diffraction, here is what it can do. This is a diffraction image of lanthanum hexaboride collected with the full beam and the detector at 90 millimeters. When I lowered the divergence of the beam, actually I used the lowest divergence available to me. This is what I got. So these larger rings that I would get with the full beam became split thinner beams. In terms of the intensity versus 2 theta plot, this is what I got with the full beam. Nice spectrum, no problem, with the alpha 1, alpha 2 split for the high resolution peaks here. But with the lowest beam divergence, this is what I got. Now I've got more peaks at lower resolution that also show the alpha 1, alpha 2 wavelength split. All right, so to finish this presentation, I will present one more cool tool that you can mount on the XtaLAB Synergy-S. It is called the XtaCheck-S. And this is a tool that you mount directly on the goniometer. It has a bracket into which you can slide crystallization plates. And this is used for batch screening. So the XtaCheck-S is a computer-controlled plate scanner designed at first for in-situ batch screening of protein crystals, and then, given you have a certain degree of freedom along omega, you can also actually collect partial dataset. So although it was primarily designed for protein crystals, you can put in the wells whatever you want, including powder samples. So typically you would load the crystallization plate sideways in its vertical position so that the wells face the beam. And then once the plate is fully inserted into that bracket, then it's held tight in there thanks to spring-loaded clamps up here and down there. Then on the second picture, you see how powder samples mounted in a few wells look like. And then on the last picture here, you see how the omega or how the omega axis can actually rotate to some extent, even though that the XtaCheck-S is fairly bulky. So the amount of rotation of omega rotation is automatically decided upon by Chrysalis Pro according to the detector distance and according to the well that is in front of the beam. And Chrysalis Pro does that because it has its own dedicated collision model for the XtaCheck-S, so you don't have to worry about collision possibilities. So the little experiment I did is that I put some silica powder into one well and some lanthanum hexaboride powder into another, a different well. And then I centered into the beam one area of that powder sample. So to center it, I just clicked on the feature that I wanted to bring into the beam, and Chrysalis Pro automatically moved the plate along X and Y to bring that feature on which I had clicked onto the crosshair, which represents the center of the beam. Now, I want to mention one more thing here, is that those the grains of these powder samples are so small that even when I brought the plate vertical, those powders did not fall off the well at all. Now, if the grains of your powder samples are larger, they will be heavier, so they are more likely to fall off indeed. Not to worry, all you have to do is put a thin layer of oil inside the well, and so that the powder samples stick to it. Then you switch to the powder data collection dialog. And again, this is the only thing that you have to know in Chrysalis Pro to collect powder or to collect with the XtaCheck-S. I'm not going to get into details here, but once you have set up the XYZ coordinates of the feature that you want to analyze, and that you have set up your data collection parameters in here, including the exposure time, you can then analyze or screen that sample right away, or you can put it in the queue via that button add here. And you see there's a panel here that will be filled up with all the samples that you put in the queue. In my case, I just put these two samples, silica and lanthanum hexaboride, into the queue. So I have two lines, one line of parameters per sample. You see that for each sample, the XYZ coordinates of the feature I wanted to screen are recorded here. I implemented a different exposure time for each sample, because for different samples, you usually want different settings, and so on and so forth. I'm going to finish this by showing you the actual data I got from silica and lanthanum hexaboride put in those wells of the plate. Here is the spectrum I got from silica. And here is one of the diffraction images I got from silica directly in the plate. And then the last slide is about lanthanum hexaboride. The data here show the higher background. And here is one of the diffraction images I got from lanthanum hexaboride collected directly in the plate. All right, and I'm going to stop here. I want to thank you for your attention. I hope I have convinced you that the XtaLAB Synergy-S is good enough to collect powder data, and that it has some benefits. And among those benefits, are the small amount of samples that you can analyze, the fact that you can run Gandolfi type of data collection. You can resolve your diffraction features quite well via this slit beam divergence control device. And lastly, you can even do batch screening of many powder samples at once by putting them into wells of a crystallization plate. So I'm stopping here. Thank you again. And I will now use the next few minutes to answer some of your questions.